thank you very much for the invitation. It's really an honor for me to be there. It's great to see everybody's faces. I mean, I wish I could be there in person, but this is also great to be here. Yeah, so today's talk is not going to be very technical. I'm just going to introduce what we do in the Computer Security Division at NIST. And also I'm going to talk about mainly of course, the lightweight cryptography project, but how we get there, a little bit of history and what we achieved over the years and what we plan to do next. And okay, so yeah, I'm leading this lightweight cryptography team, this project, and it's been a very, very long journey. We started in 2015. And in February of this year, we had a big milestone of announcing the winner of this competition. And so we are towards the end, so the final steps of this process. Okay, so in the talk, I'm going to have like 4 parts. The first part is talking about NIST Computer Security Division. So a little bit of overview of what we do there. And talk about the lightweight crypto standardization process, how we evaluated the finalists and selection of the winner. And finally, next steps, what we want to do next. So this is a picture from our campus in Gaithersburg, Maryland. So this, I mean, this campus is not as big as NIST, but it's still very big. And I don't know if you can see my cursor, but this is where the Computer Security Division is. It's pretty big. So by the way, do you guys see this menu? Is there a way for me to hide this?
Yes, it is seen, the slideshow, resume slideshow menu.
You only see the slideshow?
Yeah, slideshow, yeah, on it.
Okay. Okay, so yeah, NIST is part of US Department of Commerce, and it was founded in 1901, so it's actually an old organization. Initially, it was known as National Bureau of Standards, especially prior to 1988. So this was a time when NIST selected the data encryption standard, so first public encryption standard. At that time, it was known as NBS. And its mission is to promote US innovation, competitiveness by advancing science and measurements. And we have around 3,400 federal employees and 3,500 associates. So it's actually very big. And but we have chemistry building, chemistry departments, physics departments. There are a lot of divisions that do research on fire, or we have a nuclear reactor in the campus, so it's actually very broad. And NIST has multiple laboratory programs, and one of which is like, we have 7, and one of them is the ITL, Information Technology Lab. And the Computer Security Division is one of the divisions in ITL. Okay. So this is where I work at. And in Computer Security Division, so everything that NIST has done related to cryptography is done by this division, Computer Security Division. And we are about like 35, 40 people, including guest researchers and administrative staff. So among these like 7,000 people. So we're a small group. And how NIST develops their crypto standards. So we sometimes do international competitions. So I know many of you are familiar with advanced encryption standards competition. So this was a big competition where a lot of universities and companies joined to select the cryptography standards that is still used today. And this was done in 2001. And after that, NIST saw that actually having international competitions, like engaging with community, was extremely successful. I mean, it's very transparent. We have a lot of interest from the community. there are, people publish their PhD thesis, so it's actually very good way of building standards. So NIST did the hash function competition SHA-3, and after that we did there's still ongoing 2 projects, post-quantum cryptography and lightweight crypto standardization, that are similar to competition. So when I say competitions, it's like paper submission to conferences. So there is a call out, and then people submit their algorithms and claim that and justify why they are strong. And then they are all published in our websites, and people try to break their own algorithm and analyze their all these algorithms. And then we have rounds, like after like a period of time, in the second round, we have less number of algorithms to look at, and some of them are eliminated, and finally one or multiple algorithms are selected. So this is how the competition works. And NIST also sometimes does adoption of existing standards. So there are other standardization organizations like ISO or IEEE, IETF. So they write standards, and sometimes we adopt their standards. So RSA digital signature or HMAC specification for message authentication codes are examples of that. And we also have sometimes open call for proposals. This is the model that we use for approving block cipher modes of operation. So if you develop a new mode for block ciphers and claim that it's actually very useful for a specific application, you can propose this to NIST at any time. It's not like part of a competition, and NIST considers these as they receive the proposals. And if community thinks, there's always a public comment period. If the community thinks that it is actually useful, then NIST may approve this algorithm. And we have 3 different types of main publications. So Federal Information Processing Standards is FIPS. These are typically used to specify crypto algorithms, like approved cryptography algorithms, like AES, Advanced Encryption Standard, SHA-3, or the new PQC algorithms are all standardized with FIPS. And additionally, we have special publications. These are the publications where we write some guidelines, technical specifications, and recommendations. They still provide requirements on how to use these approved algorithms. And we also have these NIST internal or interagency reports. These are mostly research findings, like we did some research that support the development of a FIPS, so we also publish these IRs, internal or interagency reports. So these reports are always public, so you don't have to pay for any of these. They are written in English, and they all have public comment periods. So once NIST published these, especially the federal FIPS documents, we have 3 months, 6 months, sometimes public comment period, and then get some feedback, and then publish the final version. And this is, have multiple principles how we develop the standards, and transparency. We want the transparency. We think transparency is very important, being open, integrity, technical merit, global acceptability, and the others are very important principles that we want to follow during this development. Okay. So most of you are familiar with the advanced encryption standard. So this was the standard. This is a block cipher, and it was selected after a competition in 2001. So, there are a couple of documents that I listed here, and so the economic impacts of advanced encryption standards document says that actually the development of the standard has this huge economic impact, over $1 billion to NIST, so that to US economy. And this was, so these are just example of reading material that were, that I would suggest to the new students. And also the development of advanced encryption standard that was written in 2021, it's very recent, explain how the standard was written and how the internal decisions were made. And we also had recently a review of the standard. So NIST started reviewing its own standards because, you know, this standard is 20 years old. We have standards that are older than this. And NIST say, okay, let's periodically review these standards so that they are up to date. Okay, so we have advanced encryption standards, but why do the crypto community continue designing new symmetric key primitives? So, you know, AES has been around for a long time. It's now we still assume that it's very secure. And why do we see new and new symmetric key primitives? I mean, there are like over 100 new designs that I see over the last 10 years, maybe. And one of the reasons is we now have new applications. So we want to preserve the format of the encryption, for example. So this is useful if you're encrypting the credit card numbers and you want the encryption to look like numbers. Like, so that, for example, if you have an old database that you store the social security numbers or like ID numbers in Turkey, and you want the database to still work after encryption. So this format encryption, format preserving encryption enables you to encrypt and keep the format of the original data. So this is something you can't do with AES. So you need something additional. And we want to search the encrypted messages, like, so without decrypting. So this is another feature that some of the new applications would benefit. Sometimes we want to order the preserve the order of the encryption, like you have ages, for example. You just encrypt them, but you want to see who is older than the other or which number is bigger than the other. So this is another feature that people might be interested in. And so there are some additional, so white box cryptography, ciphers used in protocols like multi-party computation. Oh, by the way, yeah, sorry. Multi-party computation, full disk encryption. These are some of the new applications. And some new additional features that we are interested in is, for example, nonce misuse resistance. So nonce is a value in crypto where you assume to use once. It doesn't have to be unpredictable, but you only use it once as like a message number or count as a counter. So sometimes in algorithms, for example, AES GCM, if you reuse the nonce, you lose security. So we don't want this because people might actually misuse nonce in real world, and this would be a problem. Another new feature people might be interested in is combined functionality. So I want to do an authenticated encryption, and I also want to do hashing, but I don't want to get two independent algorithms. So I want to have one algorithm that can do, AEAD authenticated encryption and hashing together, and maybe a MAC together. This is another new feature that people are interested in. And recently we talk a lot more about side channel resistance, right? And having inherent side channel resistance is an important feature as well. So this is usually achieved having nonlinear layers that can be implemented with small number of AND gates, small number of nonlinear gates. And And we sometimes care about related key security, post-quantum security. There is a new concept of key commitment, RUP security. This is release of plain text security, and being suitable for constrained devices. Okay, so having one standard algorithm that fits, that you could do all of these applications, have all of these features is not possible. That's why we initiated the lightweight cryptography project to find algorithms that are suitable for constrained environments. And so our main motivation is we all started to see these constrained devices in our lives, like these RFID tags, the sensors, or IoT devices. They're small, very small devices. And we started using them in new applications like home automation. So some of us have Alexas in our house. We use these in healthcare. Sometimes we measure our health data, and in smart cities, they are actually everywhere. They sense information, they take information from the environment, and typically this information is private. It should be private. I mean, where your current location is, and your pulse, your blood pressure, these are the information that we want to protect. But we see that when we started this project, most of these information that we assume that is protected is actually not protected, and we think there are many multiple reasons for this, but one of the reasons that we can identify and actually solve is that we don't have good cryptography standards that are suitable for these devices, these small devices. And most of these NIST standards, like Advanced Encryption Standard, the hash functions, SHA-2, SHA-3 families, or a public key side of these algorithms, they're all optimized for general purpose computers, not necessarily for these small devices. And how lightweight primitives different from like conventional algorithms? And we still have this trade-off, right? This security, performance, and cost trade-off while designing a primitive. So you want it to be secure, but you can't really have, so many rounds. So the algorithms are usually iterative algorithms. So you have a simple round function, and then you repeat it over and over again using a different key every round. So it's easy to find a secure algorithm, but we also want the performance to be good and the cost of implementation to be also acceptable. And in lightweight crypto and earlier designs, it was, okay, let's use shorter keys. Let's use shorter block sizes, smaller security margin. So this was the approach. But after having a lot of research on, designing lightweight cryptography primitives, we see that actually we don't need smaller keys. I mean, we don't need so small block size. We can actually do a lot more intelligent than that. So the new designs are typically having smaller, simpler implementations, simpler iterations of simple rounds. Like, for example, AES has this 8-bit to 8-bit SBox. So this is an SBox where it's very complicated if you want to, implement it. You typically need, I think the best implementation of an AES SBox, you need 32 different nonlinear gates. But now those new designs have actually very, very simple nonlinear layers, and also the bit permutations, which is basically 3 in hardware, but you repeat more times. And it's basically a challenge, an engineering challenge to design a lightweight primitive, but you have the same concern. You have the security, performance, and cost trade-off, but cost is a little bit more restricted than conventional algorithms. And also, we say lightweight algorithm, and what we mean by a weight of an algorithm is the property of its implementation, right? And and it can be measured with different kind of metrics, and it really depends on the target platform that you have. So if you have hardware applications, or if you're going to implement your algorithm in hardware, then the main metrics that you are interested in is the area, latency, power consumption, and throughput. And if you have, I don't know why it doesn't say that. If you have software applications, you are most interested in the code size, RAM usage, and the memory usage. Okay. So NIST hosts multiple workshops and on lightweight cryptography, and we decided that, okay, let's have a public competition-like process similar to the AES and SHA-2 and post-quantum cryptography. And we looked at different applications, we get some feedback from the industry. We say, okay, we're going to develop new guidelines, recommendations, and standards for optimized devices. And our scope is going to be authenticated encryption and optional hashing for constrained software and hardware environments. So what is authenticated encryption? You do encryption, but in addition to encryption, you also authenticate the data. Okay, so this is a symmetric key-based algorithm. And we also wanted hashing as well. Okay, so in 2018, we decided to publish submission requirements and evaluation criteria. And our deadline was February of 2019. And this call included the security requirements, so what we are looking for, the design requirements, and implementation requirements. So this document is available online, so you can take a look at it. And we said, okay, your keys need to be at least 128 bits, but for lightweight cryptography, we allowed the designers to claim a security level of 112 bits, slightly less security level. And especially for applications that need to process a lot of data. So we wanted to have this gap. But the main design requirement is for the algorithms to perform better than NIST standards. And mainly our benchmark is for, we are mainly comparing with AES GCM, AES using the mode Gallows counter mode, GCM, and as the hash function, we also think about compare with SHA-2. So this is the fastest algorithm, that hash function that NIST had. And we had some requirements on implementations, like you have to have a specific API, and some you have to, the input-output sizes has to satisfy some of the requirements. Okay, how did NIST evaluate, plan to evaluate the algorithm? So the evaluation criteria was actually very complicated. So we had many different things that we looked at. Of course, the security of the algorithms is the most important criteria. How mature are the designs, the design principles, the underlying components, what are the security claims, are there any security proofs, and they also look at, of course, the third-party analysis. And then the whole purpose of lightweight cryptography standardization is performance. So we looked at software and hardware performance. And we looked at some target devices. For software, the main target devices are microcontrollers. And we also want the algorithms to be flexible for, if you have a 8-bit microcontroller versus 16 versus 32-bit, the design should be flexible enough that it gives you opportunities to do different optimizations. And also side channel resistance for software performance as well. And similarly for hardware, we looked at FPGA and ASIC performance, how they compare to NIST standards, again, flexibility and side channel resistance. And there were some additional features that we looked at. misuse resistance. Like if you use an algorithm with that violates in the internal assumptions of the design, like if you reuse the nonce of, or if you use dependent keys, one key and the next key that you select as actually not selected independently, maybe you have a counter for the keys. So these are the things, what happens. This is an additional feature that we looked at. Ease of standardization, ease of implementation, ease of standardization, design diversity, especially diversity compared to NIST standards, and post-quantum security of the algorithms were the main evaluation criteria. Okay, so this is like a timeline of where we, of the project. So we started in 2015, and now we are in 2023. It's been like 8 years already. We had multiple workshops. Initially to get like the first and second workshop was mainly to get feedback from the industry. Then we published a report on lightweight cryptography, and then we announced it. We received the finalists, we received the candidates, we announced the first round candidates, and after each round, we published a status report explaining how we made the eliminations. And in June, we will have the 6th lightweight cryptography workshop. So the deadline was yesterday, but if you're planning to, this is a virtual workshop, so you can attend if you want to. Okay, so as I was saying, the evaluation of the candidates that were submitted were done through rounds. And so we had total of 3 rounds. In the first round, we had 56 candidates and 56 first round candidates. And we evaluated them based on their security. And in the round 2, we have 32. So this round 1 was like just it took only 4 months to eliminate from 56 to 32. And then in the second round, we had 32 candidates. It took around 20 months or so. And then round 3 from March to February 2013. So it's almost 2 years for round 3 as well. And yeah, so the evaluation criteria in each round was a little bit different. In the first round, we only looked at the security, and we see that there are some candidates that are not secure enough, so we just eliminated those to focus on more promising candidates. In the second round, we were all able to see some performance metrics, and in the final round, we had a lot of hardware, software benchmarks, and including protected implementations. Okay, so these were after the evaluation of second round, we ended up having 10 finalists. Ascon, Elephant, Gift, and up to Zodiac were the finalists of the algorithm for the competition. And although they were like 10 algorithms, each finalist was actually a family of algorithms. So each finalist included multiple submissions. So for example, Ascon submission included 2 AAD algorithms and 2 hash algorithms, and also additional non-official ZOF submissions. ZOFs are like hash function, XOF, where you can specify the output length. So it's not the only difference from hash functions is in hash functions, you have fixed output sizes. In ZOFs, you could select the output size, okay? And that becomes very useful primitive. And then for example, Elephant has 3 AAD variants, but not a hash variant. And some of them has just 1 AAD, 1 hash. The key sizes were mostly 128, but Sparkle family included 256-bit version as well, in addition to tiny gender. Yeah, so these are the main input output sizes, the keys, nonce sizes, and output tag sizes. in the hash function variance, the digest size. It's mainly 256 bits. So when we have large number of algorithms, especially in the beginning, 56 algorithms, we wanted to categorize the algorithms based on different properties. And so some of these algorithms only provided authenticated encryption with associated data, AEAD, and some of them provided AEAD and hashing. So we did grouping of these algorithms. And for permutation-based designs, designs that use permutations as their underlying primitives, it's actually very easy to have an AEAD and hashing together. And whereas in block cipher mode, the algorithms that are based on block ciphers, stream ciphers, tweakable block ciphers, we are mostly having them in AEAD only. So in the final round, we have 5 algorithms, 5 submissions that provide only AEAD, and the remaining 5 AEAD and hashing. And permutation-based algorithms were almost half of the submission beginning for each of these rounds. Okay, so we looked at the designs, we looked at how they, their internals, how they compare to each other, and we also did a lot of software benchmarking. So this was the team, in this team, doing the software benchmarking, but we had independent teams that does software benchmarking on different platforms and slightly different metrics, which might give you slightly different results, but they were all consistent for their conclusion. So the algorithms that shined in one benchmarking team also had very good performance in others as well. So it wasn't like they are independent results. Although they looked at different devices, different metrics, there was a lot of same conclusion from all of these teams. And we had different number of software implementations available for each candidate. So some of the candidates like Ascon had over 120 implementations for AEAD versus like Brain has only 6. So if you have optimized implementations dedicated for specific microcontrollers, that actually shows your, that is very good for your design. It just shows the potential of your design very well. So this is like all of the results that software benchmarking. We have to be a little bit careful, that having a fair fair comparison of these algorithms is hard due to many reasons, but one of them is availability of software implementation. Some teams provide many implementations. Some teams only provide a few. Okay. Yeah, so in the benchmarking by NIST, we looked at code size, execution time, and combined sizes. I'm going to skip there. So, for example, the smallest AEAD, we looked at the flash size in bytes. The first, so this blue, orange, and green represents only the encryption code size, decryption code size, and what happens if you want to encrypt and decrypt together, what would be the size of your implementation. So this is ASGCM, which is the NIST standard, the first one. And we have Ascon, Tiny Jumbo, and Zodiac performing better. It's just having smaller code size. And this is another platform, 8-bit instead of 32-bit. We still have, Ascon, Photon Beetle here, Tiny Jumbo, and Zodiac having smaller code size. And for hashing as well, SHA-256 is the NIST standards to beat. And we have, in this platform, Ascon is doing very well, and Photon Beetle not so well, but in another platform, if Photon Beetle, this algorithm has an optimized implementation for this AVR, it actually has a lot better performance. Yeah, we also looked at the execution times and compared it to AES for different message sizes. So each of these numbers show the message length, and the y-axis show you the associated data length. So this is the data where you don't encrypt, but you just authenticate. And we looked at short messages and we compare it with AES. So for this, for example, Ascon, for the implementations that we have, is approximately 30 times faster than advanced encryption standards. So this is a huge improvement. And similar to, so blue represents very good, but if you have some reds, it says it's kind of slower than our current standards. These, we have some extra slides. Maybe I don't have to focus on all of these, but yeah, this is code size, again, in another platform, comparing the finalists. And here we have AES UCM, where this is the NIST standard, and all of the code sizes for this platform for the candidates are significantly smaller than AES. We also looked at hardware benchmarking, but this was done by an independent group, not by the NIST group. They looked at many different metrics like throughput, latency, throughput over area, and they have constraint on the, excuse me, they had constraints on the area, and these were the results. These are the results from the second round benchmarking, where we had 32 algorithms. Okay, so having a fair evaluation of finalists is very challenging. And I mean, the main challenge comes from, we had, in the beginning, we had this evaluation criteria figure where we had different metrics. And assigning different metrics for each criteria is hard. And justifying this. And the design came with different security claims, different functionalities. There were attacks with different complexities. And also, not all of the algorithms received the same amount of attention from the crypto community. So these were the main challenges that we have. And all of the decisions that was done was based on publicly available analysis and benchmarking results. And in February, NIST announced Ascon as the winner. So among these 10 algorithms, we selected Ascon, mainly because a large amount of third-party analysis. So we had a lot of analysis, we had internal analysis of Ascon. We looked at, in different scenarios, how we can attack it, and in non-misuse scenarios, we still think that it has a very large security margin. And it has a significant performance advantage over NIST standards in software and hardware. The design was not changed since the beginning of the competition, and even before, when it was designed in 2014. And there was another competition that was not designed by NIST, but it was a group of international cryptographer led by the university. There was the Caesar competition. So it was also selected as the winner of this competition. So this was an additional approval for Ascon. So we ended up selecting Ascon, but the thing is not over. So right now we're about to publish the third round status update, explaining the details of how we made the selection. And in June, we're going to have this virtual workshop where we discuss various aspects of standardization. Okay, as I said before, Ascon is not just one algorithm, it's a family of algorithms. And it has additional features that was not even part of the competition, but it just comes with the design. So this was not part of the requirements. So these are the things that we are going to look at, like which AAD variants to standardize. All of these variants or a subset of them? Are we planning to standardize a ZOF, this extendable output function, or a hash function? What to do with additional functionality like dedicated max? And what are the additional parameter sizes that can support? How about larger nonces? So these are the things that we will discuss in the workshop. And after the workshop, we're going to draft the standards, so publish these standards. So this is what we plan to do next. And so we have a public forum, emailing forum, LWC forum at NIST.gov. So we have around 800 people. So we frequently get emails there. And we have a GitHub website where we include all of these software implementations, and our project website includes all the information as well. Okay, I think this is all I wanted to say about the project that we have at NIST. And NIST has multiple other projects. And I mean, some of the other projects that I'm working on is random number generation. So NIST, ODTÜ has a lot of experience on randomness. We have, Ali Doğan Aksoy and his students made a lot of contributions. So this is another project NIST has. And I'm also working on password-based key derivation functions and AAD, another AAD project we have. The VO, HMAG. So we have a bunch of other projects that's going on. So if you go to NIST website and see a project you're very interested in, you can communicate with me if we can see if there's something you can do from Turkey, or you can visit us for a short time, and I can give you some information about the different opportunities that NIST provides. I think that's all from me today. Thank you very much for invitation and paying attention.
Thank you so much, Meltem. That's so nice presentation. So this is now question session. So is there a question? Any questions from participants? If you have, please raise your hand, or you can send via chat screen, chat.
Okay, let's see. Hoş geldin mesajı. Yeah, so what are you guys working on? Maybe I can ask you.
Thank you, Meltem. It was a very, very nice and inspiring talk, because that also shows how the approaches to creating the projects. And it's very nice of you to mention that we can collaborate. I mean, I'm not from that area. As you mentioned that the random number generations, my question to you is, if I know that there are algorithms related to improving the random number generators, but what are the most commonly used ones recently?
Yeah, so when we talk about random number generators, there are two different worlds, let me say. So one of them is the random number generators that rely on physical events like the temperature or like your hardware interrupt times. So we collect randomness from the environment. And we have dedicated hardware random number generators based on ring oscillators, like maybe I shouldn't go into details, but it's the part where we generate randomness from the environment, like, or your mouse movement. So you move your mouse, you provide some randomness. So collecting those randomness is one part. At NIST, we call them entropy sources. And then we have this, once you have a little seed, like 128-bit, 256-bit, that is random, you plug in those bits to a deterministic algorithm, and then you generate long sequences of randomness. So the second part is fully deterministic. So these are mathematical algorithms where you, NIST has currently 3 standards for that based on block ciphers, hash functions, and MAC algorithms. So they are very cryptographic algorithms where you iterate number of times. But how do you combine the entropy sources, the actual randomness that we grab from the environment, and these pseudo-random number generators, and output something that can be used in cryptography as your key, secret key? That is kind of the challenge. We looked at the whole space. So you might have a coin that is biased. You just throw the coin, but you don't get ones and zeros with equal probability. With these, there are biases. Or you have a coin that provides you an dependent results based on what you received previously. So yeah, it's a little bit challenging when you look at the whole space, but when you look at just the deterministic part, NIST has like hash DRBG is an algorithm that we use, a pseudo-random number generator. We have counter DRBG. It's also block cipher based. So we have multiple pseudo-random number generators that are available in one of the standards that we have.
I assume that their return period, just starting to repeat themselves, is enlarged as well.
Yes, so they have very large period, but they are eventually periodic. Like the period is typically 2 to the 128 or 256, but NIST never allows them to be used like that. You always need to reseed these algorithms from the randomness that you collect from your entropy source. So you generate a sequence and you have an internal state, you load some more randomness to the device or the algorithm, and you generate randomness again. So it's never like you get a random value from somewhere and you plug in the pseudo-random number generator and generate the whole thing. It's like for each call for the random number generator, you just reseed. Sometimes you forget so what happens if the internal state is captured by the attacker? So NIST has a lot more additional constraints if you want to use a random number generator as to use for cryptography.
There are a couple of special publications published by NIST. So what is the next step in standardization of RNG or PRNGs?
Yeah, actually, we are hosting another workshop in end of this month, like May 30 to June 1st, I think. So feel free. This is a virtual workshop. So we basically have 3 standards: 90A, 90B, and 90C. 90A is about, this is SP 890A. So SP means that special publication. The first part is about pseudo-random number generators, like everything deterministic. You have a seed you achieve from somewhere, and then you generate the output. So we are currently revising that standard. We have another part, the second part, entropy sources. This is all about the physical thing. Yeah, nothing like cryptographic. It's more like, okay, you capture randomness from some physical phenomena. So that's where the entropy sources is. And the third part of this standard is, okay, how do you merge these two? Like you have deterministic random number generators, it's the pseudo-random number generators, and you have the entropy sources, how to combine this. So 90C is about that. We also have 822, which is mostly what you guys are most familiar with. It's like you are giving a sequence by statistical hypothesis testing. Is this random or not? So that is also, I mean, that's not very useful in cryptography terms where most of the outputs actually pass these tests. So passing these tests is not enough to be used for cryptography, but it's still useful in, in evaluation your RNG. You can still get some information about it.
So those terms will be revised on 90A.
Yeah, A, B, and C. They're constantly working on this. I think the project has been going on over 20 years, and there is always things to learn from the industry. So we write the standards. We have every week we meet with BSI. BSI is another organization in Germany, very similar to NIST. And they also have random number generation standards. So they work in a different model. The country, they have a different type of validation programs. So we'll be meeting with them very frequently so that the standards are aligned. And we want to make sure that a random number generator that passes their validation passes ours as well, and similarly vice versa. There's an ongoing research needs to be done, and yeah, and a lot of open problems as well. This is very different from regular, cryptography algorithms. So you can't really. It's harder to test, harder to justify, harder to implement.
Thank you. Thank you, Meltem.
Questions?
There is one more question from here, from the classroom actually. So go ahead.
Okay, hello, I'm Adusa Javed, and I have a question that is there any competition that have the implementation like optimization of these lightweight cryptographic primitives without compromising the underlying security? So is there any competitions in the coming days or in future?
So we're not actually planning for a new competition, but the current competition we had that I described included looking at optimized implementation. So we requested optimized implementations from the designers and also from everybody who wants to implement this. So they send us implementations, and we looked at, some implementations were optimized for code size versus area in hardware or latency. So there were many different metrics. And currently we're not planning on another competition for this implementation. So all we need to do at this point, we selected Ascon. There are some minor decisions to be made, like parameter sizes and, including of different variants. Once the standardization is done, so once we write the standards, it's always useful for us to have new optimized implementation, but not necessarily within the competition.
Okay, and the second question is, during the evaluation of Ascon, do you have any implementation of Ascon which have side channel resistant?
Yeah, so I did not actually include this in the slides, but there was another independent third-party group, also George Mason University, who did the hardware benchmarking. They organized a protected implementations study. So they requested protected implementations and checked whether the implementations were actually leaking any information about the key or not. So all of them are available in George Mason University's website. So we have protected implementation, masked implementations for Ascon and many other finalists.
Thank you.
Mm-hmm.
Anyone else? So maybe I can ask one question, maybe Meltem. So you mentioned somehow ease of standardization.
Yeah.
So what does that mean?
So, let me go here. one of the, for example, one of the algorithms that we received was AES with 8 rounds. Okay, so we have the AES with 10 rounds, and the algorithms, the submission was AES with 10, like 2 less rounds. And that's actually very hard for us to standardize, right? It's like you have 2 standards, one is for 8 rounds, one is for 10 rounds. It really doesn't make sense, and it would confuse people. And we think that that wouldn't, I mean, that's also a little bit attached to that design diversity. And some of the algorithms we had, like, instead of having a round structure, it has 3 and 4 different rounds. The algorithm was very complicated, and the, you know, security comes, for that algorithm, the security came from the complexness of the algorithm. It was very complex to, you know, for the first 4 rounds do this, for the next 5 rounds do, and totally different operations, and for last 5 rounds do something else. So these are not good for standardization. It's really hard to write the standard. It's really hard to justify why the algorithm is secure. And it's hard to implement one in the real world as well. So those were the algorithms we kind of eliminated.
So can we say that this is from point of view of NIST? So it is
yes,
somehow
exactly. This is the point of NIST. So how would it be easy to standardize? And also another issue about this is IP issues. So intellectual properties. So some of the algorithms came with IPs. So it wasn't easy for us to write the standard, and it was not possible for companies to use the algorithm without paying money to the companies. So that was actually something like we didn't want in lightweight cryptography standardization. So I mean, if we had one algorithm that were very, very good and had an IP issues, maybe we consider the whole picture, but having an patented algorithms is, it's not easy for standardization. We just need to communicate with a lot of lawyers, and, it's always on the side of NIST.
Yeah. So, for instance, for the number of available software implementations, are they all supplied by the designers, or did you get them from the public repos?
Yeah, so we looked at multiple repos. Let me see where. Yeah, so you see there are different benchmarking groups, and some of them implemented all of these finalists. Like, I think Renner, he implemented all of these finalists. He included his implementations as well. So we looked at different repos, GitHub repos. We collected all the implementations, and we have a lot of implementations submitted by the designers as well. So it's like a combination of those. See, we have over 500 different implementations.
So NIST only implemented 8-bit and 32-bit microcontroller implementation,
yes,
software implementation.
Is
it possible to have a verified implementation like eBag? So can NIST serve such a service so that those implementation could be verified and that can be used for evaluation?
Yeah, so what we did was we have a GitHub web page, which I included in the last slide. So all of these implementations that we looked at are here. All of the results are here, but and all of the optimization flags that we used and the metrics that we used are here. The only thing I think for verification is to just go over that, and if you have a similar device, you could just run the same things on your own device and see, you can compare. But there are a lot of things that makes a difference, minor difference, like optimization flags or the input sizes. So if you do everything similar, I think it would be possible to verify.
It's so we can consider like that this is a community collaborative work. So not only done by NIST, but also by other implementers. So this is a community work from academia, industry, and all around the world. So somehow we converge to some points.
Exactly.
Any more questions or comments? If there's no, so let's thank again speaker Meltem.
Thank you. Yeah.